first law of thermodynamics, the conservation of energy. So, the energy in the universe is constant, is the summary of what the first law of thermodynamics is. But just because energy is constant, what you can have is energy can change form. So, for example, you can have potential energy converted into kinetic energy. Where recall that potential energy is stored energy or energy by virtue of the object's position, and kinetic energy is the energy of motion. So an example would be potential energy would be me sitting here recording this playposit. There's potential energy and by virtue of my position sitting, and then that potential energy can be turned into kinetic energy if I get up and go to teach class or whatever. So energy is changing. So energy is conserved. The amount of energy in the universe is constant, but that energy can shapeshift, can change form. Mathematically, what that a form of the first law of thermodynamics is this equation: delta U, where delta U is the change in internal energy. So the change in internal energy. Sometimes you'll see that written as delta E. Just be aware of that. But change in internal energy can be either delta U or delta E. And Q is heat. So heat is a concept that you're probably familiar with. And W is work. So work. Energy is defined as anything that has the capacity to do work. So, work. For this chapter, work is often associated with pressure volume work, work that gases can do. Before we can get into that, we've got to figure out signs. So sign conventions for heat and work describe where the energy is flowing from. And every thermodynamic system has a system and the surroundings. And energy can flow into and out of these two entities. Chemists are primarily interested in the system. The system is often the chemical reaction, so often the chemical reaction, or it is a phase change. For example, a solid being converted into a liquid, melting. So using that example, to get the idea of tracking energies, heat and work, when you have a solid converted into a liquid, that process is melting. You've seen this happen when ice melts and turns into water, liquid water. Solid ice is H2O, and liquid water They're all H2O. So melting. So when an object melts, a chemist defines this as the system. So in order for that to happen, energy goes into the solid from the surroundings to melt the ice, to melt the solid. So this would be an example. So heat Q going from the surroundings into the system. And then from the perspective of the system, the sign for Q is positive. Energy goes in. For the surroundings, Q is negative. Energy goes out. So energy going out of a thermodynamic entity, the sign is negative. If energy is going into the thermodynamic entity, the sign is positive. So some key terms to get the sign conventions right. So work done on the system. Okay? So the system, that's our perspective. Sorry about that, I'll edit it out. Work done on the system. That means that the word on, so the system is the object of the work. So work being done on the system means the system is receiving it. Therefore, the sign is positive. Work done by the system, the next term. By the system. Okay, the system is doing work, performing work. When you work out, when you work, you perform, you get tired. So energy is going out of you, or energy is going out of the system when you do it. So that sign is negative. Heat absorbed by the system. This is a little bit easier to understand, but absorbed is going into the system. Okay. Absorbed. Be like sitting next to a fire. You're sitting next to the fire. If you define yourself as the system, you're feeling that heat, you're absorbing it, you're getting warmer, energy's going in. The sign would be positive. Then released, the energy's going out. If you picture in the wintertime, you can see this when you exhale, and you can see your breath. Part of that is the breath that is leaving you is warmer than the outside air, and energy and heat is going out of you, out of the system. But the sign conventions are important for the types of calculations that you'll see in this chapter. So here's a typical example of a calculation involving the change in internal energy that you'll encounter in this chapter. So the formula for change in internal energy is Q plus W, where Q is heat and W is work. So that formula. And another important thing to write down for a thermodynamic problem is what is the system? it's asking what's the change of internal energy of the fuel. So we're looking for delta E of the fuel. That is our system. So we have to look at, is the fuel doing work or being worked on? Is the fuel creating heat or is it absorbing heat? The fuel is the perspective. So Q is heat. Let's read the question again. It says, if the burning of the fuel in the potato cannon performs 855 joules of work on the potato and produces 1422 joules of heat. So heat is Q. That's 1422 joules. We'll make a decision about the sign in a moment. Work. Go back and read. The cannon performs 855 joules of work. So we've got the numbers written down. Now it's the tough part. What are the signs? So the potato cannon performs 855 joules of work. Okay. The potato cannon, the fuel in the potato cannon. Okay, so the fuel is the system. The fuel is performing work. Okay. If you perform work, do you get tired? Or, well, that's a bad example. Work does energize some people, but so when you do work, though, energy is coming out of you, okay, in a fundamental sense. So if energy is coming out of the fuel, okay, it's going from the fuel to the potato. So that sign is going to be negative. The fuel is doing work on the potato. The potato is the object. So the fuel, from the perspective of the fuel, is negative. So next, heat. It produces 1422 joules of heat. Again, the potato, or the cannon, the fuel in the cannon is producing heat. Okay, producing it. So making it. So it's coming out of the fuel. The sign of heat is negative. Now that we've got those signs, we can solve. Those negative values. If I do that math correctly, that's negative 2,277 joules. So the fuel created the energy. The potato and the surrounding air absorbed it. So the fuel was the source of all of the energy. It came out of the fuel.